Are you live?
We're good? All right. Hello, everyone. Welcome to the Geography 1 lab review. This is for the final exam. And so your final exam is comprehensive. It's going to include material from labs 1 all the way to 9. And so tonight we're going to review material from labs 6 through 9. If you want to review anything from labs 1 through 5, you can go back and watch the midterm review. It has all that information for you from 1 through 5. Tonight, we're only talking about lab 6, 7, 8, and 9. So let's go ahead and get started with lab 6. Lab 6 is atmospheric pressure. So we're going to talk about the atmosphere. So in lab 3, we talked about the atmosphere and all the different layers. And then in this lab, we talked about the atmosphere's pressure. And that pressure is caused by gravity pulling the weight of the atmosphere to the Earth's surface. So that is what atmospheric pressure is the weight of the atmosphere being held to the Earth's surface by gravity. And you remember from lab 3, the atmosphere, we kind of refer to the atmosphere as that big ocean of air. So atmospheric pressure is just that big ocean of air being held to the Earth's surface by gravity. Now our pressure is going to be strongest closest to the Earth's surface because gravity is strongest closest to the Earth's surface. And so all around here closest to the surface is the strongest higher pressure. As you get away from the surface and you head out deep into the atmosphere, the pressure gets lower and lower because gravity is weaker and weaker, and it's not, that force isn't holding onto the air molecules as tightly as it was before. And so your pressure is lower on the edge of the atmosphere. And there's two factors that go into pressure, and the two factors are density and temperature. This is important that you know these two factors, density and temperature. They're shown in this formula called the ideal gas law. This shows the relationship between the density and temperature and how it affects pressure. So P is pressure, R is just a constant value. Then we have our density and our temperature. And so in this formula, if one of them changes, if one increases, the other one is going to decrease and be affected. So one increases, the other decreases, and vice versa. So this just shows the relationship. You don't have to use the formula to calculate anything. It's just showing you how density and temperature can affect atmospheric pressure. And so kind of to go a little bit more into that for density, if you're talking about density of air molecules and relating to pressure, that's pretty much just talking about how tightly packed the air molecules are. So are they very dense where they're very close together and tightly packed, or is it less dense and they're very free-flowing, floating around air molecules with lots of room? So that's what it's talking about for density. And then temperature is pretty easy. That one's just whether the gas molecules are hot or are they cold, and that's pretty much what it means for density and temperature here. Next is how to measure pressure. We measure it with this instrument called a barometer. It looks just like this. It has the atmospheric pressure here in units called millibars. That's how we measure pressure, is millibars, also known as MB. You can also use the unit pounds per square inch, but for our labs, we use millibars. And so here on the barometer, it has kind of a lower pressure here, and then it kind of goes up and up and up and up. And then you have a high pressure over here. And also notice on this barometer, it talks about having rain or fair weather. So if you have lower pressure, it's more likely to rain. If the pressure is higher in the air, then normally it's a little bit better, nicer weather. So that is measuring pressure. Also on here, it talks about the average sea level pressure, and that's going to be 1,013.25 millibars. So that's our average sea level pressure. Now that was measuring pressure. This is mapping pressure. We map pressure with lines called isobars. And so all these different lines on this map are isobars, and they represent equal areas of atmospheric pressure. So this line right here, for example, this isobar represents 1,008 millibars of pressure. So everywhere on this line, so from California, this line all the way through to Texas, and then through Mississippi and the little corner of Alabama, all of this is 1,008 millibars of pressure. And then The next one is 1012, so they go by intervals of 4. So 1008, then 12, then 16, 20, and so that means anything in between these lines is going to be in between 1009, 1010, 1011. That's what those numbers are going to be in between these lines. So looking at this map, you can kind of guesstimate what the pressure would be for any of these states. And then also talking about isobars, depending on how they're grouped together, they have what's called troughs or ridges. So here we have a trough. These lines, this black line is our isobars, and you see in the center of our isobars, it has a big L, and that L represents low pressure. And so anytime you have a grouping of isobars and the center is low pressure, and you have these groupings, it's called a trough. So this is a trough, this grouping's a trough. All of these are called troughs because the center has low pressure. Over here, the center is an H for high pressure, and so these groupings are not troughs, they're called ridges, and they're shown with this zigzag line. So ridge, here's a ridge, these are all ridges. Over here, troughs are shown with a dotted line. So if you have a weather map, like a James Band shows a weather map, and you see these zigzag lines over the isobars, then you know that that's a ridge. So that's how isobars kind of show areas of pressure, whether it's high or low. Okay, so one more thing for Lab 6, talking about this lab. We talked a little bit earlier about how closest to the Earth's surface, where gravity is strongest, we have all these red circles represent our air molecules. So closest to the surface, you see they're very densely, tightly packed because gravity is strongest, so it's holding them there with a stronger force. As you go up in altitude away from the surface, gravity weakens. And so as that force weakens, you see the gas molecules start to spread out. So they're not as dense. And so there's actually kind of a way to calculate it, sort of, but every 5.6 kilometers you go up in the atmosphere, the pressure divides in half. So here, this is kind of a really fun fact. I like this fact, I think it's interesting. So at 5.6 kilometers from the Earth's surface, so that's really not that far. I think it's about 3-ish miles. So about 3 miles off the Earth's surface. If you're that high in the air, you'll have 50% of all the atmosphere's air molecules below you and 50% above you. And that's not talking about the distance of the atmosphere. That's talking about the air molecules, the mass of the atmosphere. So 50% of them are below you because gravity is holding them there tightly, and then 50% is above you because they just have all that space to be free and float around. And so that just shows you gravity's force, how it's a lot stronger on the surface and then much weaker as you go up in altitude. So those are the main points for Lab 6. As we go through this review, we're mainly talking about the things that are going to be on the exam. If you notice while we're going through a lab, we don't talk about a certain topic, that means that it's not on the exam. So we're really reviewing the things that you need to know for the exam. So I think that's it for Lab 6. So now we're going into Lab 7, atmospheric moisture with Miles.
To update this real quick, James and I made some changes. Okay, good, yeah, my changes are there now.
Yes.
Well, welcome to Lab 7, atmospheric moisture. If you're keeping up with your lab manual, we're now on page 55. So here's some of your key terms just to kind of keep in mind. Your atmospheric moisture, your humidity, and your absolute humidity. Do keep in mind the difference between your humidity and your absolute humidity. And then also, remember, we have specific and relative humidity. So specific is the mass of water vapor in an area, relative is the ratio, and if we go back real quick, humidity in general is just the amount of water vapor, and water vapor is important because it causes rain, or precipitation, as we like to talk about in my class. And your absolute humidity refers to your density of water vapor in that chosen volume of air. Remember, the air parcel It's gonna be your Minecraft brick. So, okay. Here's your sling psychrometers. This is many you got to go out and experiment with. The sling psychrometer, you swing it around, and it has your wet bulb and your dry bulb. And as your wet bulb is drying, it's going to do so directly proportional to the amount of water in the air. So again, our sling psychrometer is what we use to measure the dew point in temperature and relative, or dew point temperature and relative humidity. That's what our sling psychrometer does. So if there's a question that asks you about that, you know the answer to the sling psychrometer. And we know that when we have our measurements, the larger the difference will tell us the difference between the wet and the dry. That'll be the lower relative humidity. Okay? Be familiar with the depression of the wet bulb versus the air temperature to find your relative humidity. So it's going to work a lot like Battleship. You go down temperature 72, say your depression is 10, you'll have a relative humidity of 57. So just, again, be familiar with how to use charts. Here's your dew point temperature chart. So it's going to give you your depression of the wet bulb. Remember, here's our wet bulb, and the other side is going to be our dry bulb. So just know how to use a chart. If you know how to use a chart, you'll be fine. So remember albedo. I think it was the last question on this lab from your hand-in assignment, on lab 7. So albedo is a percentage of solar energy reflected from the Earth's surface. If you have a really light surface, a lot more that's going to be reflected. It's why you want to wear lighter colors when it's hot outside. If you have a lower albedo, means you have a darker object that's going to absorb and retain most of that solar energy, while you wear darker colors in the winter. So yes, that refers to, remember we talked about if you're standing on the asphalt versus if you want to stand on the grass in the summer, which would be cooler, the answer would be the grass because it's not as dark as your asphalt. Any questions so far?
None.
Cool.
None.
Okay, adiabatic lapse rates. This section got a little bit confusing in my lab. I think we're following the example, yeah. This follows the example from, no, this is the example we did in class. So this example should look familiar. So adiabatic lapse rate. So the adiabatic just refers to the rate of change in that parcel of air as it undergoes change in elevation. So as it's moving up, we're down. We're going to see that mountain in a second. So as the arc parcel goes up and down, what does that change? So our dry adiabatic lapse rate, word dollar, is 5.5 per 1,000 feet. Remember, it's important to know how much you're moving. It's not just 5.5 no matter what. It's if you're going up or down, and 1,000 feet is our typical ratio that we're looking at. Then we have the Waller, or the wet adiabatic lapse rate, which is 3.2 per 1,000 feet. So when we apply that to an example, here we have our windward and our leeward. Our windward is going to have our clouds coming in with that moisture. And so we know up here is where the moisture is. So that means down here, probably not going to use the Waller. We're going to use the dollar. So I'm going to run through this example a little bit with y'all, but if you're watching this later, pause it and try to do this yourself, because it's a very good example of how to go through this. Any questions so far?
None.
Okay. So first thing we're going to do is we're going to look at where we're at. We're at 70 degrees Fahrenheit at 0 feet. We're going to go up 1,000 feet. Wow, what a great ratio. So if we're going up 1,000 feet, we see no clouds because our clouds represent our moisture. That means we're going to be dry or wet. It means we're going to be dry. So 5.5 per 1,000 feet. So as we're going up, we're going to be subtracting. It's getting cooler. So we're going to get 64.5 degrees Fahrenheit. It is important to know Fahrenheit. Always put your unit. Some professors and lecturers might take off credit for not having your unit. So we've gone up 1,000 feet. Now if we're going from A to B, again, 1,000 feet. Do we see any clouds? No, we don't see any clouds. So we know it's still dry. We're still using the dollar. So that ratio is still going to be 5.5 per 1,000 feet. We get 59 degrees Fahrenheit. So this one's a little tricky, and I think some of y'all struggled on this on my lab. So we're going up to C. So between B and C, there are no clouds. So right now we're still using the dollar because we haven't hit the moisture yet. It might not always be as clear, but in general, in this example, again, the clouds represent moisture, humidity, and wet at a backlapse rate. So we're going to see, we're still using our dollar. Still dry. So we're at 53.5 degrees Fahrenheit, and then we're gonna go up 1,000 feet, but those pesky little clouds, they mean moisture. Always have been. So we're gonna switch over from our dollar to our waller. It's gonna go to 3.2. It's getting cold still as we're going up, but it's not getting cold as fast. Strange how that works. So we're gonna get 50.3 degrees Fahrenheit. And now we're going all the way down back to our 0 feet. So we're going from 4,000 feet, so it's more than 1,000 feet. There's two things to remember, is that we're going from 4,000 to 0, and also that we're going down the mountain this time, which means we're going to add. So, do the math, think about it for a second. Think about how you're going down, so you're adding. And also think about, are there clouds over here, or are there no clouds? If you do that correctly, you should get 72.3 degrees Fahrenheit. So, it's interesting to look at how the temperature has changed from leeward to windward, or vice versa. So yes, we've gone down 4,000 feet, and that's what we got. Any questions? I know we're kind of quickly on that math. No?
Nope, none, John.
Well, that's all I got. Do I need to update you real quick? Did you
What's up?
add,
Oh, no, you're good. Right here.
did you add anything?
I did, but it's here.
Did you add anything since I started?
No.
Okay.
No.
Just checking.
All right. Well, students, severe weather. Let's talk about it. All right. So severe weather, page 63 in your lab manual, by the way. I highly advise actually reading through your lab manual. There's a lot of good stuff in it, including ways to pass your test. So, yeah, pro tip, reading is fundamental. Please do that. All right, let's get talking. So, we talk about severe weather. We have to start talking about air masses. And they're large, right? Really large. So an air mass is something that will be a mass or a large grouping of precipitation or moisture, and it will have a specific temperature to it, and they will move over continents. We are not talking about something that is small on a town or state level. We're talking about something that takes up entire countries in this case. And we are talking about air masses. So they are distinct from surrounding air parcels, which means that if you go and you are in one air mass, but then let's say you travel a certain direction, you will go over to another air mass, and they will be completely different. You will be able to have marked differences between them. And they are typically only formed over uniform lands and seas in high and low latitudes. I know in my classes I like to talk about making spatial references. So in this case, we are talking about equatorial, right? A lot of these form over the equator or the tropics, and areas that are Arctic or above. Okay. So let's continue. So we generally have 5 types of air masses that we are talking about. There are more, and your book actually talks about 2 more that are in here, but we're going to talk about these 5. So we have the maritime polar, and again, I also like to talk about where words come from. So when you hear the word maritime, I want you to think water, right? I want you to think water. So this is cold water polar, right? Cold water polar, basically, or water cold polar, right? So that happens over the northern Atlantic and the northern Pacific for us. Right, and then you have the maritime tropical. So again, we got the maritime, which means water, okay? And that happens in the tropical areas, the tropics, if you will, okay? And then we have the continental tropical, okay? Continental tropical. So this tends to be in areas that are in lower latitudes, but over continents. And tropical, you're mainly going to be talking about how warm something is, right? How warm something is. But continental Arctic is exactly what you expect. It's over the Arctic Circle, right? But it is continental in nature. So that means it's very cold, it's typically over land, and then continental polar is going to be a little bit below the Arctic, right? Right here. Any questions you got so far? No. Didn't even look. What types of air mass would be most common in each of the following cities? Well, we're talking about Jacksonville, Alabama, right? Where we are right now. So we start right here. We are typically maritime tropical. This is why we have very warm, moist weather almost year round. Almost year round. Okay? New York City, and New York State is going to be in the North Atlantic, right here. So you will have this area, which is going to be your maritime polar. So Miami, Florida, which is like right down here. Going to get your maritime tropical, much the same. Stop that. Much the same as we will get here. Santa Barbara, California. So SoCal, right down here. Right. So you see maritime tropical. Okay. And Shickety, Montana. Shickety, Montana. If you've ever known how to say his name, this is how you say it. Shickety, Montana. And that's like up here somewhere, and it's cold. So it's continental cold. So, all right, stop that. So let's talk about cold fronts. So there's going to be three types of fronts, 4 types of fronts we're going to talk about. Lisa. I don't know. Did it? Well, we're going to keep going. This forms when cold air displaces warm air. Did?
Yes.
Whatever, let's talk about fronts. We're doing this. So, thank you. If you've ever been in my class, you know that it's a comedy of errors. So the comedy continues into the reviews. So, fronts. Fronts happens when 2 air masses collide. When they smash together. And a buffer zone is created. A buffer zone is created. This is typically a narrow band that exists between the fronts, and they move in the direction of the strongest air mass, and they displace weaker air masses. So think about this. Remember when we talked about the movement of air, about air pressure, right? So remember that high pressure flows towards low, right? High pressure flows towards low. And we often see this with a high pressure will have more power to it, and it will displace the low. And you'll see that happen here as well. This is dependent upon heat, direction, and moisture content. So if you have a front that might be warmer, but it has a lot less moisture content, it will be pushed out by a front that is colder, but has a lot more moisture. There will be more mass, literally more mass to the air to push, right? Let's talk about those. So we have the cold fronts. Here's the first of the 4. It's cold fronts. They form when cold air displaces warm. Cold air displaces warm. This results in heavy rain and rapid temperature drops. And what happens when the temperature drops? The relative humidity rises, because remember that temperature and relative humidity are inversely related. You must know that. And the dew point temperature is reached. This is what tends to happen here in the early tornado seasons here in Alabama, is we will have days where it will warm up in the spring. It will warm up in the spring, but then what will happen is it will start to cool down, and that cold air will come rushing in, and it will create instability and bring with it heavy rain and rapid temperature drops. So, talk about the next one. If we had cold, we're talking about warm. So this is what happens when warm air displaces cold air. And warm air is unstable, so it brings with it rain, typically when these move in. And they tend to create these shallow horizontal clouds. So if you're ever outside and you're like, wow, today feels warmer than yesterday did. You go outside, you can look up, and if you see these long, kind of like horizontal clouds running through the sky, this is typically a sign of a warm front moving in. Right. So again, also take note of the way these are symbolized. So warm air will be red, right? Warm air will be red and typically has these like strange little like ping pong ball looking things. I don't know. Almost looks like Digletts from Pokemon. I don't know. Kind of like Digletts. But the cold air has these teeth, right? Cold air has teeth. It's got that bite, winter's bite. So, all right. But let's talk about a stationary front. So, what happens when the unbreakable sword meets the unbreakable shield? Well, they just kind of hang out there. So, you will see that when you get a stationary front, it is 2 masses of typical or somewhat similar mass will come together, and they will just create a buffer zone that results in a mixture. as neither one of them is overpowered. And typically what happens is one of them will eventually exhaust its energy and the other will take over. But in this case, you will see a mix with teeth and, you know, little Pokemon Digletts here, you know, these things. Yeah, all right. Last one, the included front. These are complex fronts. So this happens when a cold front overtakes a warm front. And this is when the cold air cuts in and cuts off the warm air from the surface. So this is what happens when these two fronts meet, and this typically results in very dynamic weather. But let's start talking about that dynamic weather, because I'm not trying to give you a full lecture here, but that's not here. Well, you have to know some stuff about, I think we have questions about the enhanced Fujita scale, don't we?
In chat?
No, in the, on the final.
Yeah.
Yeah, please know that, just in case, just know it. So, everything from pages from the hurricanes, please read through those. Those might not be on it, but just to be safe, study everything. Study it all, so you know. All right, let's move on. We're talking climate graphs. Let's talk climate graphs. All right. So this is the most recent one. And this is about classifying climates. Classifying climates. So another important distinction to make here, and all of my students that I have, I almost require them to know this by the time it's all said and done, is the difference between weather and climate. It's the difference between weather and climate, and I show my students a video of Dr. Neil deGrasse Tyson walking his dog, but I will summarize that is if you are walking your dog down the street, right, the path that you take is the climate, it is the trend, the movement that you make from one year to the next. Try to imagine every step you take is a year. But you don't stand there and take a step in various directions. You don't do this when you walk. You walk in a straight line. Right? But your dog might decide, well, I want to know what's going on everywhere. So your dog will kind of zigzag around you, going from one thing to another. But it will always be tied to you. It will never go too far in one direction because you are always hanging on to that dog. And that is the way that climate and weather work. So climate is a trend, right, an average of years, where weather is what is happening day to day. So we classify climate based off of temperature and precipitation. And this is driven by averages. As I said, when you are walking that dog, every step you take is a year. So when you start averaging those years up, what path did you take? And that is how we measure climate. And we use three, what we call degrees here. I don't want to get you confused here. There's three classifications to measure climate degrees. And let's talk about that. Yeah, so you'll get this in class. I will at least be handing one out. You will get this in class. You will need to know how to use this. And the three classifications we have start with the major classification, right? The major classifications range from tropical humid, right? Tropical humid to dry to mild mid-latitude, severe mid-latitude, and polar. I highly advise that you go back and you read over some of these, what these do, and also how these function. I will start to elaborate here. But the first major climate group will be the one on the far side of your chart, right? And you'll have the big capital letters, and you must pay attention to what case you are putting in these. So you have your tropical humid, which is your wet low latitudes, right? So think of this like equatorial regions. Your dry, this is not latitude specific. I talk to my students about how you can have a desert without having a desert. Well, how do you do that? Well, you go somewhere really far up north that doesn't get a lot of rain. You can have tundra regions that are like this, right? Where the evaporation exceeds precipitation, but it is still blisteringly cold. So it's not tied to latitude. And then we have the mild mid-latitude. Mild winters or warmer hot summers. That's us. We're right here. That's us. We are mild mid-latitude, as is most of the east coast of the United States. Then we have severe mid-latitude, which is very cold winters. This tends to take up a good portion of Europe. I don't think a lot of people understand just how far north Europe actually is compared to the United States. But this takes up a lot of Europe. Where polar, well, this should make sense if we've talked about Antarctica and the Arctic Circle. This is where stuff like this exists. High latitudes and very cold. So once we have the major group, we start talking about precipitation. And this is where you have to pay attention. Notice case, right? Uppercase, lowercase. Pay attention to these. Be very clear. But you notice that we start to get into kind of we have some conditions here. We have some conditional letters here that you have to look at the chart or what you are, the data you're working with, and figure out where these rainfall totals are. Okay? And you will see that we have over 40. So it's wet year round, typically over 40. That typically happens in equatorial regions because it's typically very wet, especially around South America or parts of Indonesia, Oceania, where you can go from monsoonal, right, with extremely wet summers. So if you see a climate graph, that has almost nothing going on in terms of rainfall in the winter months, this is what's happening. It's probably monsoonal. If you also see rain, then a lot of rain happens in the summer months. Then you have dry in winter, rains in summer. Again, these are conditional. Dry in summer, rains in winter. So again, you will have to check that chart. Then we get into the uppercase letters. Arid desert. Arid desert. So this is like the Sahara, the Gobi. Areas around the world that their evaporation, the amount of water taken from the environment, exceeds what is given back. So then we have the semi-arid steppe. So greater than 10 inches, but less than 15 inches. This encompasses a good portion of Africa and some parts of the equatorial regions and islands around the oceanic area. But then we do separate the northern regions into two different things. So the ice cap, this is the ice cap, right? So an ice cap would be an area that is just covered with ice. It's just covered with ice. But a tundra will actually be an area where soil is exposed, but the water is trapped in the soil, right? So be sure to note precipitation, and the last one, temperature. Temperature, and this is where things can get a little complicated. I will tell you, just a little tip for you, sometimes it is good to work backward with these. It is occasionally good to work backward. See what you can get, and if you note that some of these classifications are not in maybe what you originally thought it might be when you look at the first column, this can tell you a lot. I generally tell my students to start here. Start here with temperature and work backwards. So we got to hot desert or steppe, and we start getting into every one of these has a conditional classification. So every one of these has a conditional classification. So be sure to note the temperatures. And remember, we are working off of averages. We are working off of averages, but here it is asking you for specific months that occur. All right. And this is a map. This is a map of the world and where some of the climates are. I pretty much got on my soapbox for my students and said how a lot of this is changing, and it's mostly our fault. Okay, it's our fault. If you don't think it is, I'm sorry. I hate to push your bubble, it's true. But here, you will see that a lot of these, where they are located, and you will note that some of them, I believe this is the desert areas. Is this tropical? Okay. So we have tropical here, but that's over here. Just over here.
Equator.
So yeah.
I know the same.
Colors are hard, man.
It's blue.
So colors are hard, man. So, all right. So climate graph. Climate graph. Also, if you're one of my students, you still owe me one of these. Most of you do. Just so we're clear. All right. Climate graph has a few things you need to know. The first will be the climate classification. So I can tell you that this one was taken from my hometown, Philadelphia, Pennsylvania. Right? So it's a CFA climate. Secondly, what you will need is look at your x-axis. And this right here is the months of the year, starting with January and ending in December. But the complicated part here, and I think where I see a lot of people get hemmed up when they do this, is the y-axis actually has two values that you need to chart on the y-axis. So look at these here, and you will see that blue is tied to the blue measurements here. Okay, so you will note that the precipitation is charted on the right side, and you will see that it is done with bars. Okay, so bars. But on the left side is temperature. Temperature denoted in the color red, and you will make a very small line graph out of that for us. So that is 2, 3, 4, 5 is the bars, and 6 is the line. So, all right. Let's look at some of these. Let's look at some of these that can help you start to understand how these work. So you note here that you see that in the summer months, which is what this is, right? The summer months here, their summer starts pretty early in April, as typically does ours. And you will note that it is pretty hot the whole way up through July. But in August starts to cool down. I'm sorry, this is precipitation, my bad. Man, I'm sitting here just explaining this all wrong. Thanks for correcting me, friends. Dude, I totally explained this wrong, students. We got this. Life is hard, okay. This is the precipitation. There's more precipitation in these months, but you'll notice the temperature almost never changes. It is pretty steady year-round. And let's look at another one. Oh, there's 2. Hey, we got 2 for this one. So note that looking at this one, we noticed our precipitation totals are, well, there isn't a lot. There's like none. So also note they flip the axes here too. This is precipitation, temperature, it's fine. So you know that this is a desert region, right? This is a desert region, and you also see that it is very hot, right? It typically does not get below 60 degrees in this region. So it is hot almost year round. But here again, we have another desert region in Nevada, right? And you notice something very different about this desert region compared to this desert region. The temperatures are much higher, right? That is because of its proximity to the equator. But here the temperatures are much lower. This is in Nevada, so this is roughly, I think, 36, 38 degrees north parallel. And you note that there is very little precipitation, but it also is very cold. It's like 30. It doesn't really get above 70 there. Pretty cold. So, all right, one more. This is Antarctica, and something's missing, but it's not actually. There just is none. So there is no noticeable or measurable precipitation here in Vostok Station, but the temperature. Take note of the temperature. Negative 85 degrees. It does not get warmer than negative 25 degrees here. I can almost promise you this has actually gotten warmer since the last time this was taken. But it's cold and nothing happens. So, all right. Well, that's it. Well, friends, if you have questions, please message your lab instructor. In fact, just message your lab instructor just to say hi. So just do it. Do it. Clog their email for me.
No.
No, don't do that. I'm kidding. Okay. Just not me. No, especially me. Anyway, so if you have questions, please email your lab instructors. You will have your final next week. And if you're watching this later, it's like April the something. I don't know. It's not this week. It's the Monday after this was posted. So April the 21st. The 7th. They're giving me baseball signs and I'm not noticing them. So I think I'm supposed to steal third base. So, all right, students, good luck, and please study.